All right, hello and welcome to a Unit 2 full review guide for AP Calculus AB/BC. This is a re-upload of the previous video because I skipped a topic and I cannot afford to skip a topic because that topic can't show up. So I'll be fully re-recording the video and redoing all of this. So here we go. Starting at topic 2.1, defining average and instantaneous rates of change at a point. So let's assume 2 points x comma f of x and c comma f of c are points on f of x. Then their average rate of change, right, or the slope of their secant line is given by this, f of x minus f of c over x minus c. Or if we let h be, c minus x, no, x minus c, then we just have f of c plus h minus f of c over h. So h is just the distance between x and c. And both of these formulas for average rate of change, you need to know, obviously, and they show up in the derivative. In fact, we're going to use it right now. So the derivative of f at c is denoted as follows and defined as. So we have the Leibniz notation, which is df over dx, and you could put at x equals c, right? That's at a point, which is the same thing as saying f prime of c, and it's defined as the limit as h approaches 0 of f of c plus h minus f of c over h, or an alternative form, the limit as x approaches c of f of x minus f of c over x minus c. Very important that you know this because they might ask you in a way like, if the limit as of this, f of 2 plus h, whatever, they might give you either write the limit form or they might give you in limit form and you have to recognize that it's actually for the derivative at a point and then apply derivative rules. So here's an example. Find the average rate of change over the interval bracket 1 comma 3 bracket of f. And we have these 2 points, right? So this is literally just like algebra, really, nothing complicated. Just take f of 3 minus f of 1 over 3 minus 1, which is 3 minus negative 5, so plus 5 over 3 minus 1, just 8 over 2, which is just 4. So that's also the slope of the secant line, right? And the other one, given f of x is equal to x cubed, express f prime of 2 using the limit definition of the derivative. So remember, our c is equal to 2, so we're going to write the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. And this is the limit as h approaches 0 of x cubed, right? So 2 plus h cubed minus 2 cubed over h. Um, and in fact, in entering topic 2.2, we can define the derivative as a function itself, right? And use derivative notation. So the derivative of function f, right? Which as a function itself is f prime of x for any input x, and it's the limit as h approaches 0 of f of x plus h minus f of x over h. It's the same exact thing, except instead of c, we're just replacing x, and x is our input. Now, you need to know all of these notations, okay? The ones I added are optional, but the ones you need to know are dy over dx, which is Leibniz notation, f prime of x, which is I think is Lagrange notation, and y prime, right? So the prime is more Lagrange, but you do need to know as well. You have Newton's notation, you have df dx, which is the same thing, or you could just put prime and parentheses, the whole thing. All of these are equivalent notations, and they all mean this. That's the definition. Now you need to know that cold, but what is the derivative actually saying? Because we want to analyze what is a derivative. Well, a derivative is basically asking for a linear approximation of a function. I think that's a really good interpretation, right? More importantly, a linear approximation, the slope of the linear approximation, right? We could create the line, the tangent line, which happens to be a linear approximation, but we're looking for the slope. And the slope of that is the derivative. So as we zoom in, right, a curve, any curve can be approximated linearly by some line. And that line has a slope, right? We talked about how straight lines have slopes. So we're going to take 2 points, x and x plus h, comma, f of x plus h, right? And we're just going to take this, line, the line between them, right? And this is an approximation for the function. Now, it has some error. It's not a perfect approximation, but it works. But in fact, as we take h getting closer and closer to 0, this approximation becomes really good local at x. All we're saying is that we can approximate the curve at x by taking h as h approaches 0, right? That secant line will now become the tangent line as the distance between the 2 points approaches 0. And of course, if we take our average rate of change formula, which I'm going to use this one, and we're going to get the difference quotient. To consider the slope of the tangent line, we need to consider what happens to the difference quotient at h approaches 0. Now we know limits still thanks to unit 1. And we need to know that this is just saying the limit as h approaches 0 of that. So that's how we derive there. You do need to know that it is a linear approximation at a point, right? The tangent line. And more importantly, the derivative gives the slope of the tangent line. Um, that is the most important part that you need to know. And one example of a problem you might be asked is to find the equation of the tangent line, which is again the linear approximation, right? This is going to come up later. To f of x is equal to 1/4 x squared at x equals 2. So the very first step is to find f prime of 2. We're going to use the limit definition because we haven't discussed properties, but of course this won't be assessed. Um, and you could look at the following algebra, but you're going to get 1, and that's your slope, right? We have the slope. Now a line we can express using point slope form. So we're going to find f of 2, which is, our y coordinate, y1, and f of 2 is just 1. And now we're going to use point slope form, y is equal to y naught plus m times x minus x naught. Plug everything in, and y is equal to x minus 1. So if we look at the function, x minus 1 is a very good approximation for the function at the point 2. Now, topic 2.3. This is, I think, the topic that I skipped before. Almost did again, but we're not going to do that. So you're going to be asked to estimate derivatives of function at a point. Graphically, you could just pick the closest approximation to the derivative of f. Now, they're not going to ask you crazy hard problems. They're going to be super straightforward, like absurdly simple, because it's not going to be asking like, is it 2 or is it 2.5? It's going to be -4 or 1/4, right? Blown out of proportion. So at x equals 2, right, this is this point. Okay, well, if we think of the tangent line, we have these two, we have this tangent line. And again, like I said, we could think about a linear approximation. So we could like approximate it to be like this line, right? This slope maybe. Um, and basically, I don't know, if this clicks, but that looks like 4. That looks like a slope of 4, right? It's not -4, it's definitely increasing. It's not 1/4 because 1/4 would be a lot flatter, so it's definitely 4. All right, and you may also be asked, but when given a table, to approximate g prime of x at a point, right? So what we're going to do is we're going to take closest possible x values above and below, and we're going to plug in the difference quotient. So g prime of 2 is approximately g of 2.1 minus g of 1.9 over 2.1 minus 1.9. Um, and you can compute that actually, which in this case specifically happens to be 4.6305 minus 3.4295, and all of that over remember, the distance between 2.1 and 1.9 is 0.2. So it's approximately going to be 6.005, but of course, if you get this, you're just going to write 6. Of course, you could put 6.005, that's not wrong, but we're going to approximate it and say it's probably 6. Topic 2.4 has to connect differentiability and continuity, right? When do derivatives exist and when they don't, right? There's a theorem, which is differentiability implies continuity, which you do need to know. If f is differentiable at a point, then it's continuous at the point. If it's differentiable over an interval, it's continuous over that interval. Differentiability is uh s- continuity is a condition for differentiability. If a function is not continuous at a point, it's not differentiable, right? That's the contrapositive. Notice that the square root of x, though, it's continuous at x equals 0, but it's certainly not differentiable at x equals 0, right? And if you think about just finding, I don't know, the slope of a tangent line, then you're going to be pretty lost, right? So instead, we have to look at the side derivatives, right? We're taking the side limits. To the left, of course, we can approximate it, and it really is just a straight line. So the whole thing, the slope is -1, but to the right, it's 1. So the limit does not exist because it approaches two different values. So that's a corner, right? Whenever we have a corner, the derivative does not exist. At vertical tangents as well, we say the derivative does not exist or it is not real, right? Those things are same. A function is not differentiable if the derivative is not a real number. However, vertical tangents you do have to keep in mind, but it's not differentiable. A cusp as well, right? This is where we actually, kind of have a vertical tangent, sure, but more importantly, we to the left and to the right, we don't have an agreement. So this is a cusp basically. And finally, standard, hopefully you should know graphically discontinuities from the previous unit, but discontinuities means that the function is not differentiable. Topic 2.5 talks about the power rule. The power rule just states that the derivative of x to the power of n is just n times x to the n minus 1. So for example, we want to find x to the power of 5, the derivative of that. We're going to drop the exponent, we're going to write x, and we're going to subtract the power by 1. Here we're going to drop the exponent, write the x, and subtract the power by 1. You should be incredibly proficient in this part, okay? Because when we get to topic 2.6, we're going to learn the constant sum, difference, and constant multiple. Now the derivative of any constant function is 0, right? The change, if we say something is constant, that literally means it does not change. And the derivative measures change, right? Rate of change at a point. So if we want to take the derivative of something that doesn't change, its derivative is going to be 0. Now, also you need to know that the derivative of a sum is just the sum of the derivatives. And if we have a constant multiple, we could just factor that out of the derivative. So knowing all of this, we can now evaluate like a polynomial, right? A full polynomial, we can find its derivative. So how are we going to do it? Well, first, what we can do is we could split it into the sums of the derivatives and factor out. So x cubed prime minus 1 half x to the fifth prime, and then of course plus 10, but the derivative is 0. And then of course this is the same as 4 times 3x squared minus 1 half times 5x to the fourth. So that's our derivative. And moving on to topic 2.7, now we have derivatives of some more complicated functions: cosine, sine, the exponential, and the natural logarithm. Interestingly, College Board introduces this at this step. You may have learned it a bit later because the natural logarithm isn't defined until you get to like unit 6. So, of course, there is that. But you should still know this when you're reviewing for AP Calculus, right? The derivative of the exponential is just the exponential. Super easy to remember. The derivative of the natural log is 1 over x. The derivative of sine is cosine, but the derivative of cosine is negative sine. You should know this off the top of your head. All right, I can't emphasize that more. Okay, so let's say they ask you to find the following derivative: sine minus cosine plus 5 times e to the x. All right, the derivative of sine, what is the derivative of sine? Well, it is cosine of x, right? And remember, we're going to use the previous rules, which is, split it into a sum, right? And the derivative of cosine of x is negative sine. So it's negative, so it's minus negative sine, which is positive sine of x, plus, and remember, we could factor out the constant 5 times the derivative of e to the x, which is just e to the x. So topic 2.8 covers the product rule, another one you need to know cold. So the derivative of a product of two functions f times g, or you may have learned it, u, v, whatever works for you. But the derivative of f times g is f prime g plus fg prime. I don't know how you want to memorize it, but you need to memorize it. So for example, find the derivative of 4x cubed times cosine x. Remember, take the derivative of the left, 12x squared, times just the right, plus just the right times the derivative of the left minus sine of x. And that is our product. So moving on, we're going to move on to e to the x times the natural log of x times sine of x. And the derivative of that is we're going to now apply the product rule, but we have multiple, right? But do not worry because we can expand our product rule, right, a bit more. How are we going to expand it? Well, I think one of the best ways to expand it is just like memorize that when you have multiple terms, you just multiply all of them and then take the derivative of one and keep going progressively in a sequence. So e to the x, right? The derivative of e to the x is e to the x times all the rest, plus e to the x times the derivative of the natural log, which is the middle term, which is 1 over x, and finally times the other one, and finally we're going to multiply everything else, right? E to the x natural log of x times the derivative of sine, which is cosine. So remember how it progresses, and you should be able to differentiate now more complicated functions. Topic 2.9, the quotient rule. Now, you do not need to know the reciprocal rule, but I mean, it could help to be a bit faster, but the quotient rule is more general. The derivative of f over g is f prime g minus f g prime over g squared. However you want to memorize it, just memorize it, okay? For example, if we want to evaluate this derivative, right, we take the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. Um, so this is going to be the natural log of x squared. Know this, know how to take these derivatives. And topic 2.10, finally, the derivative of all the other trig functions. Not much to explain here. You just need to know them cold, right? And also, maybe if this helps remember, tangent and cotangent is just going to have secant and cosecant, squared. Whenever there's a like cosecant or like cotangent, the sign is going to be minus in front. And for secant and cosecant, you're going to have the function times tangent, or for cosecant, you're going to have this function times cotangent, right? So tangent, derivative of secant squared, but the derivative of cotangent is just going to be negative cosecant squared, right? It's going to be negative. The derivative of secant is just secant times tangent, but the derivative of cosecant, right? Because we have a negative cosecant times cotangent. These are all just ways to remember it, but however it works for you, learn it. And that's unit 2. You should be able to evaluate some more complicated derivatives, but not yet chain rule. However, by unit 3, you should be cranking out derivatives like it's nothing. Okay? So good luck and keep studying for AP Calculus. You got this.